Hi, I am Shanawaz. We begin this lecture with the following proposition. So, let G is equal to S1 plus throw plus Sn, where the Si are subgroups. And the Si are subgroups. And let Ji, which is defined to be a map from Si to G, be the inclusions. Then the following conditions are equivalent. Then the following conditions are equivalent. So we have the first item. G is direct sum of these SIs. The second item, for each G sorry every G belongs to G has a unique expression of the form G is called S1 plus so on plus Sn, where Si is in little si is in big Si for all I. The third item, for each I Si intersection of Si with all Si's except Si, S1 plus so on plus. Now this Si is omitted, so we put a cap over here, plus so on plus Sn. This has to be the singleton set 0. And finally for the homomorphisms, which are in the projections, this is item 4. For there are homomorphisms Pi from G to Si for all I, and these Pi's are called projections. such that Pi Ji, this is the identity on Si, comma P K Ji, this is the zero map for whenever k is not equal to I. When k is equal to I, then we have the identity map. And finally the sum of these maps Ji Pi, where the sum runs from 1 to n, I runs from 1 to n. This is identity map on G. Now to prove this, first we are going to prove first implies second. Now to prove this, we will use induction on n. We prove this by using induction on n. The base step is true for n is equal to 2. We have already proved the result. Now assume that the result is true for up to n. We are going to prove this true for n plus 1 as well. For the inductive step, for the inductive step, set t is equal to s1 plus so on plus sn, so that g is equal to t plus sn plus 1. Now what we have done here, we have assumed that the result is true for n. That is, we have assumed that each element of t is uniquely expressed as an element of s1 plus an element of s2 plus so on plus an element of sn. Now we have defined g to be equal to t plus sn plus 1. Now by case n is equal to 2, each g in G has a unique expression, of the form G is equal to little t plus sn plus 1, where t is in t and little sn plus 1 is in big Sn plus 1. But by the inductive hypothesis, this t is in t and the case is true for n. So but the inductive hypothesis says that T has a unique expression. T has a unique expression of the form T is equal to S1 plus so on plus Sn, where these little si's are in big si's for all 1 less or equal to I less or equal to n. So this proves that this little g can be uniquely expressed as s1 plus s2 plus so on plus sn plus 1. So this is obviously true. Now the case second implies third. Second implies third. This follows from the previous lemma. This is actually the previous lemma. This follows from previous lemma. Now third implies fourth. Now we are assuming that Si intersection this all sum of si's except si is 0, and we have to prove these inequality and these equalities. So by the lemma, by previous lemma, by previous lemma, we may assume item second. So by previous lemma, item second is true. Now if this is true, thus uniqueness of expression says that this uniqueness, because item second is about the uniqueness of the expressions, thus uniqueness of expressions says for each I the functions pi from g to si are well defined. This is given by pi of s1 plus so on plus si plus so on plus sn. Now this is the element of G, and pi maps this element to the ith component, which is this little si. So this is this little si. So this uniqueness expression says that this these maps are well defined. Now to prove these equations, we have now see ji is the inclusion map of Si into G, and Pi is the projection map of G into the Si component. So Pi Ji will be a map from Si to Si. Now let us see what this map is going to do. Now Pi Ji is a map from Si to Si, such that Pi Ji, now here this is the composition here. Now when we operate it on some element, say Si of big Si, we get, now this Pi, this is Ji of Si. Now this Pi, now this Ji, this is just the inclusion map, so this is simply Si. Now this Si has the expression like this, it is 0 plus 0 plus so on plus plus Si plus so on plus 0. Now this Pi is the projection map, and this maps this element to the Si component, so this is simply Si. So it takes an element Si and maps it onto Si, so this Pi Ji acts as an identity on Si. Therefore Pi composed with Ji, this behaves as an identity map on big Si also. Now let us consider the map PKGi. Again, Ji is the inclusion map of Si into G, and this is Ji, and Pk is the projection map of G onto Sk. Now it is given that I is not equal to J. Also Pk composed with Ji is a map from Si to Sk, such that Pk of Ji, let us see what is going to happen to an element Si of big Si. So this is Pk of, now this is Ji of Si. Since Ji is the inclusion map, this is same as Pk of Si. Now this Si can be expressed as 0 plus so on plus 0 plus Si plus 0 plus so on plus 0. Now this Pk is projection map, and this element over here is non-zero only at ith component and 0 otherwise. So it is kth component where k is not equal to I is 0. So this is nothing but 0 since k is not equal to I. Therefore Pk composed with Gi is the 0 map for all j not equal to, sorry, k not equal to I, for k not equal to I. It remains to prove that finally Now Pi is the projection map of G onto Si, and Ji is the inclusion map of Si into G. So JIPI is a map from Ji to finally Ji composite Pi is a map from G to G, and hence sum of these maps JIPI is again a map from G to G, where is iron is from 1 to n, such that when we operate this map on some element of G, that is same as sigma iron is from 1 to n JIPI. Now each element of G can be uniquely expressed as an element of S1 plus, this is from third. We have assumed that third is true and we are proving fourth. So if third is true, then G is uniquely expressed as sum of elements of Si's. So this is sigma iron is from 1 to n. This is Ji of now this is projection map. So this map is this to Si. So this is again equal to sigma iron is from 1 to n. Since Ji of Si is Si, so this is again G, hence sigma I no ironing from 1 to n JIPI is just an identity map on G. Now it remains to prove that fourth implies third. First. Again we prove this using induction on n. We shall prove it using induction on n, where n is bigger or equal to 2. In the case n is equal to 2, which is the base case, is true because it is already proved in the previous lemma. Is true by previous lemma. For inductive step, again define for inductive step. Let us define T to be equal to S1 plus so on plus Sn. And define J to be the map, T to G to be the inclusion map, to be the inclusion, and finally define P from G to T to be the projection map by P takes the element S1 plus so on plus Sn plus 1. Now it maps it to the element S1 plus so on plus Sn. Now this map is a homomorphism. So if this is given to be a homomorphism, so by the base step, G is direct sum of T and Sn plus 1, and hence by induction hypothesis, by base step G is equal to T direct sum n plus 1, and by the inductive step and by the inductive hypothesis, T is direct sum of S1 plus so on direct sum Sn, because this was the inductive step. I mean the induction hypothesis thesis is true for n. We are currently proving that it is true for n plus 1 as well. So if this and G is direct sum of these two groups, then therefore G is direct sum of T, which is direct sum of S1 through Sn, direct sum Sn plus 1. Hence we are done in this case. So this completes the proof of the theorem.